Hi guys, Dr. J here, and in this video we're going to be talking about Green's functions. So Green's functions, we're going to define what they are. We're going to talk a little bit about what they are mathematically, but we're not really going to use them. We'll use them in some other videos, and so you'll see how they get used in those other videos, but we'll just define them in this video. So a Green's function is a function which satisfies this particular version of Poisson's equation. So we have the Laplacian of g. G is our Green's function. It's a function of both r and r naught is equal to this funny thing, which we'll talk about in a second. Now, first of all, r and r naught. These are vectors. These are just positions in 3D space, or any dimensional space, I guess. But in particular, we're going to be thinking about them in 3 dimensions, x, y, z. And so each r or r naught is just x, y, z for some particular location in space. Poisson's equation, right? We are taking the Laplacian of this function of these two variables. And the Laplacian is equal to a delta function. Now, what is a delta function? Now, a delta function is properly defined. I think it's called a weak function, and we need to use an integral to define it correctly, and it's kind of complicated. We're not going to do that. We're going to kind of use a very simple, I don't want to say it's approximation of what it's, we're not quite using the real definition here, but this is effectively how it works. We'll put it that way. Delta of x, delta function, is going to be equal to 1 where x is equal to 0 and 0 elsewhere. So it's just a unit impulse when the argument of the function is equal to 0. Now again, this is a simplification. I'm sort of glossing over some important details here. It's not quite correct, but it's close enough and it's going to work for us for how we're going to use it. So this delta function is going to be 0 everywhere except for one location, which is where that is equal to 0. And if you look up here now, where is that going to happen? It's going to happen where r is equal to r naught. So if r is equal to r naught, this is going to equal 1. Otherwise, it's going to equal 0. Now, interestingly enough, you can also notice that that reverse of that will also be the case. R naught minus r will also be 1 whenever r is equal to r naught and 0 otherwise. So this thing can actually be flipped and reversed. And that brings up an important property of Green's functions, which is related to the reciprocal version of the Green's identities. We talked about Green's second identity in a different video. Go check that out if you want to see that part. But we can show that this is the case. So basically you flip the order, and you can think about these two things, and we're going to kind of use this notation as we go along. Think about r as our observation location, our measurement location, something like that, test location. And then r naught is going to be like a source. So sometimes it's called like source location and receiver location. So r naught might be like the center of the Earth, for example. Well, it's not exactly the greatest analogy, but maybe it's the location of a point mass, for example. And that's going to make sense here because this is a unit impulse at that location. So when r is equal to r naught, we get a unit impulse, and that could be reflective of a point mass there. Right, so here's our Green's function reciprocal symmetry. And then what we want to say is, what's the solution? Like, what is the Green's function for 3D space? And we're not worried about any sources just yet, or we're not worried about any surfaces or any complexities, just a basic solution to this Green's function. And notice it's only a function of r. So there's no theta, there's no lambda. This is a simple function of distance from r naught, a radial function. So what we're going to do is we're going to use the 3D version of Laplace's equation in spherical coordinates. You can see the equations for Laplace's equation in 3D in spherical coordinates in your notes. I think that's going to be the notes for, lecture 1. But anyways, this is spherical coordinates, Laplace's equation. All the other terms drop out. Why? Because there's no theta, there's no phi in this equation. There's only r. If they're in there, they're going to be constants at most. So what we're going to have here is we're going to just notice for a second that this is the derivative of this equal to 0. This is never going to be 0, so this must be 0, which means if this is 0, this inside thing has to be a constant, right? Derivative of a constant is equal to 0. Everything else, there's going to be some function of r in there. So this is some constant, and that means r squared dg dy is equal to some constant c. Well, pretty easy to integrate this actually. And we get G is equal to negative C over R plus D. So we've got two constants now. You can see this is this constant, and then there's going to be one more constant of integration. We need to integrate both sides by R, all of that stuff, and rearrange, or rearrange and integrate, and we get this solution. If we require that the solution vanishes at infinity, this is a very common kind of boundary condition where we say, if you get infinitely far away, and again, think about this in the context of gravity. If you get infinitely far away from a point mass, gravity potential is zero. And so we want this to kind of be zero so that the field will vanish. And in that case, we'll just have negative C over R. R goes to infinity. This whole thing goes to zero. And so we'll say D is equal to zero. And that gives us C. And then we need to figure out what that constant is. There could be a constant in here in terms of lambda and phi. And we're just going to say that it's the spherical surface area. And that's going to give us a 1 over 4 pi. And actually, it's going to be negative 1 over 4 pi. And so our final solution here, and again, what did we satisfy? We satisfied this expression here, and we satisfied that the field must go, the Green's function must go to 0 at infinity. This is going to be G of R and not 1 over 4 pi. R minus R naught. And really, this is just 1 over 4 pi R. If R naught is at the origin, it's just 1 over 4 pi R. If R naught is not at the origin, then it's R minus R naught. Okay. So that's the gravitational potential of a unit point mass. That's exactly the formula we have. 1 over 4 pi R is the gravitational potential of a unit point mass. And so G is equal to 1 over 4 pi R is the fundamental solution to the Laplace's equation in 3D free space. What does that mean now? Well, we can actually use this Green's function to build solutions for multiple point sources, multiple point masses. In 2D, I'll just write down in 2D, if you're working in 2D, this is 3D, G, 2D, not. So again, these R's are just the vector locations in multidimensional space. This is just going to be the same thing, very close. Slightly different constant because we're now integrating in only one angle instead of both angles. And then log of R minus R naught. Thing to notice here, we have the 2 pi instead of the 4 pi, but in 2D. And then this negative sign makes this 1 over. So it's really log of 1 over R minus R naught. And so in 2D potential, the 2D potential field decays more slowly than 3D case because you have this logarithm in here. And again, that's related to the integral in 2D coordinates. One more thing I'll say about the Green's function is, let me get rid of the 2D case. Yeah. So Green's function in 3D, if we have an arbitrary density distribution, we can calculate the potential. So our total potential, in order to get the potential of an arbitrary mass distribution, we're just going to integrate the Green's function, which is for a particular point, over the distribution of mass, basically. So we can write that as, this is UG, gravity potential. What have I done? Green's function, which is a function of R and R naught, integrated over the density at R naught, integrated over the whole volume, times a constant, some version of the gravity constant. What do we have here? This is the Green's function. This is the point source. That's this equation here, this expression. You see that R minus R naught. So we're going to take the density at R naught, multiply it by the Green's equation for R naught, and then integrate that product for the whole distribution of mass. And this is the key thing. This is why Green's functions are so powerful, is because they allow us to take a very simple solution, just a point mass solution for Poisson's equation, and then we can substitute that into our integral and integrate over a whole arbitrary distribution. So maybe we have a really wacky shaped distribution. Maybe we have a spherical distribution, which is the Earth. Maybe we have a spherically symmetric distribution. Maybe we have some random distribution. We can deal with all of those by simply integrating the Green's function times the density function, where the density function is where the density is in space. So we have some density distribution in space. We integrate over that space times the Green's function. We get the solution for gravity. And of course, this is the exact same as this. Just the Green's function, plugged it right in there. We can do this integral over our domain. Now, notice I've done the constant. I've absorbed that into my constant out here. So this is why Green's functions are powerful. We can solve a very simple point source, basically. So the Green's function gives us the solution for a point source, and then we can integrate that over a volume to get a more complicated result. And this is basically exactly how, for example, modern day software like Oasis Montage or something like that, this is how they would calculate the response, the gravity response. So this is how modern day modeling works. And this is called forward modeling. Given a density distribution, gravitational constant, we can calculate the potential anywhere due to that distribution. All right, that's enough about Green's functions for now. I will see you in the next video.